Hello and welcome to the LMI webinar series. My name is Aaron, and today we are discussing surface filtering, the sequel, the advanced tools. And today I have with me Chris Hooper, who's our territory manager, and Michael Fisher, who's our field application engineer team lead. Before I hand it over to them, just a couple of housekeeping notes. If you have any questions during today, if you're watching this live, please use the chat function on the right-hand side of your screen. It should be a little bit down. You can ask us any questions there, and we'll do our best to answer all of them as they come in. The second part is that this is being recorded, so if you by chance have to step away, don't worry. Take a look in your email inbox to find this recording. It should show up about an hour after this. So without further ado, Chris, I would like to hand it over to you.
All right, great. Thanks, Aaron. So I think what we'll do to start is just do a quick overview of the filters that we covered in the last session, which occurred in February. So let's run through these real quick. So gap fill, median filter tool. In this particular example, we use them together. Just as a quick recap, these filters are actually not a part of the tool set, but rather just in the scan area under the scan tab on the acquisition side of the Gocator user interface. So gap fill and median, pretty straightforward tools. You can see from this example here that we've used the gap fill to close up some of these missing points that you see here in the data. This is particularly important for an application like this where we are calculating the void volume inside that container with the blocks in there. And then the median filter tool, we're generally trying to get rid of a bit of noise there. Once in a while, that noise can show up as the result of overzealous gap filling. So it's a nice way to clean up any noise that you have in there, particularly if your gap filling has introduced a little bit of that. All right, so the next one we covered was the surface curvature tool. This is a really helpful filtering tool if you are looking for defects on a surface that might have some curvature in it already. So in this particular example, it's a cylindrically shaped smart speaker. It had a plastic outer shell on it and then a mesh speaker grill underneath. In this case, we're looking for flash or maybe some overmold in the plastic on the outside. So the first step we do, apply that surface curvature tool, and that will take that cylindrical shape out of the scan data, if you will, create the flat surface that you see there on the right. And as you can see, that anomaly that we're looking for now really stands out, and we can apply something like a blob tool to identify it easily and quantify it as well. Vibration correction filter. So this one's really easy to apply. There's not much in the way of settings here. It's really just a matter of putting your ROI or search window around the area on which you want to remove the vibration. So this is, typically vibration that's going to be part of a moving conveyor type of system. So this filter is going to look specifically for waves in the data, sine type waves in the data that would be introduced by vibration. And you can see the before and after there clearly shows its removal. Again, this allows you to look for other anomalies in the scan data and not allow the vibration to cloud that. Close filter. This is a really good one, again, for closing the gaps, if you will, or completing missing scan data. This is on a circuit board. This is a very, very tiny feature. What's really nice about this is you're doing this at a pixel or kernel level. So when you're using the close filter tool, it's easy for you to maintain size of the feature that you're measuring, which is sometimes not true with the gap filling tool. This is a bit more precise. So the idea here is if you needed to apply a measurement to, say, this small boss on top of this chip here, you can use the close filter tool to close up some of these gaps while maintaining size. Open and dilate. This is, again, a great example of using a combination of filters, in this case, dilate after the open filter. So this is a VGA connector. It's an application we see often at LMI where we are trying to detect the position of these electrical pins here. Very, very shiny typically, so there's always going to be some level of noise, and you can see that in the before scan on the left-hand side there. So the open filter, we use that to kind of close up some of that noise that you see there and get rid of that. And we follow that with a dilate tool to kind of expand the size of those pins afterward, which allows us to identify their location much easier and more robustly. So again, for this application, we weren't particularly worried about the size of those pins, just the location. So that dilation of those pins is appropriate in this case. Okay, so this is a bit of an overview of some of the different filters that we have in the Gocator tool set, and they've been divided into a couple categories here. So the kernel filters to the left, these are some of the ones that we covered in the last session back in February. But what we want to talk about today is some examples of these single pixel filters, specifically threshold filters. We're going to talk about a couple of those today, percentile and relative threshold. But we're also going to talk about the direction filter, which is used for reflective surfaces often, and some of the built-in filters which might be embedded in other tools for ease of use, and some of the custom filter capability as well. So with that, I'm going to jump into the Gocator emulator, and we will look at a couple examples. Okay, so the first one we're going to talk about here is the relative threshold filter. And that relative threshold filter is embedded inside the Surface Filter tool, and it's one of the choices that you see here in the list among many others. So for this particular application, you can see that we've got an automotive piston here. We scanned this with a Gocator 3210. And what the customer was after in this case is verification of a circlip that sits in there that holds the wrist pin in place. Specifically, the customer needed to see that the wrist pin was seated all the way, or I'm sorry, the circlip was seated all the way. And one of the ways they detect that is by measuring the gap on that circlip. So as you can see, when we look at this raw scan, our scan data quality is quite good, but we've got quite a few features in this stack here. And in fact, when you're just visually trying to look for that circlip in there, it's really difficult to discern with all this other scan data here. So what we want to do is kind of isolate that circlip. That's really what we're after and what we want to identify here. Now, one of the benefits we had for this particular application is this part is really well fixtured, or would be really well fixtured in the manufacturing process. So what does that mean for us? Well, the repeatability of this piston is pretty solid in terms of position, meaning we can depend on this piston overall being in relatively the same position each time that we need to measure it. This gives us a lot of flexibility in terms of being able to create a very narrow envelope for us to focus on, and that's essential for us to be able to isolate that circlip in there. Now, one thing I'll mention is that in cases where you might have a significant amount of part movement here, we have all kinds of surface transforming and anchoring capability to be able to track that measurement with different and varying positions. So as we go through our chain of tools that's been applied here in our effort to isolate that circlip in there, the first thing that we've done is defined a datum surface in here from which we want to compare that circlip position. And we've done this through surface masking, which allows us to laterally isolate different features inside here. So this is the surface within that stack, if you will, that the customer has chosen as a reference plane from us to start. And what we mean by that is this surface we can depend on being in the same place in the fixture vertically all the time. We will generally apply a surface transform tool, although that's a bit difficult to visualize here. What we're doing is, again, we're further isolating this and we're taking out any tilt that might be present in our scan data here. So we can correct for that tilt, so we know that as we apply further tools to this, we've got a perfectly flat datum structure to work with here. And then finally, we get to the part here where we apply that relative threshold filter here. And you can see now that this circlip really stands out nice for us. And let's talk a little bit how we've done that. So if we look at the settings for the surface filter relative threshold, you can see that we've got a high threshold value and a low threshold value. So what are we telling this to do with these values here? Well, essentially we're saying, you know, I've got some datum that's based on that ring surface that I showed earlier. So that's kind of my zero starting point vertically. But what I'm saying here with this relative threshold is I only want to see the data that's between 1 millimeter and 2.5 millimeters high off of that initial datum surface. Again, since in this case we've got good repeatability on our vertical fixturing, we know that based on this this envelope here and the testing that we've done, that we can depend on that circlip showing up within that vertical region all the time. So what exactly are we doing? We're just creating a vertical envelope within which we will isolate the scan data. And we can see that in addition to the circlip, we've got some other data that's part of the what I might call the housing of the piston, if you will, around there. And we will typically use what's called a surface mask to eliminate some of that. And that allows us to really, in this case, isolate that circlip in there, which is what we're after. Now, ultimately, what we did is we looked at two different measurements on this. Once we extracted it here and converted it to a very simple profile, we can now look at the radius at various positions. Of course, if this circlip is not properly seated, these radii will be smaller than their tolerance allows. And then, as I mentioned earlier, ultimately what we are after is this gap width, because again, of course, that gap will shrink if the circlip is not properly in place. So that's an overview of relative threshold. So the next one that we're going to look at is percentile. And percentile is used in very similar ways, but depending on some of the caveats of individual applications, it can be helpful for dealing with things that differ slightly. So for this application, we're looking at, this is an automotive nozzle. There's several pieces of plastic here that are part of this assembly, and these are, welded together. The challenge with this particular application is that the customer really needed to know the planar angle of this sort of middle surface in here, right? The real challenge is that the position of all of these things, both in the full coordinate system and relative to each other, could be all over the place. There's quite a bit of variation. Now, of course, on the Gocator platform, we have quite a few tools for dealing with that sort of thing. But, if we're really after this particular plane here, and we can't depend on any of these other features being repeatable relative to it, we need to get creative in terms of isolating it so we can look at the angles of that plane. So in this case, we used a percentile filter as well. Now, just like we talked about with the relative threshold filter, this is a vertical data filtering. So I like to think about the data in a column, if you will. And instead of giving a defined measurement, an envelope that's based on specific dimensions, instead we're giving it a percentage of the pixel data within that column that we want to see. And just like we had with relative threshold, we have a high percentile and we have a low percentile. And what that allows me to do is not only isolate a specific percentage of the data within that stack or column, if you will, but allows me to drive that to a particular location within that stack as well. So you can see in this case, I've chosen between 88% at the high point, 62% at the low point, meaning I want to see about 26% of the data in that column, but I want to do it at a specific location. And you can see now that I can very easily isolate that particular surface plane in there. I can then apply a surface plane tool to that, and I get my X, Y, and Z, or I should say X and Y angles and Z offset or location vertically of that particular plane. Now, the percentile filter allows me to do this even though I can't really depend on any of the surfaces in that scan to be repeatable position-wise and use them as a datum or an anchor. So this is a great tool for isolation for some applications like this with quite a bit of variation in position. So the next one that we're going to look at is okay, one second. Next one we're going to look at is a direction filter. And the direction filter is one that I will often use for cases where you've got a very reflective part, and that reflective part is creating noise in what I might call a pattern like you see here. So on this application, we're looking at a highly polished steel plate, and the customer is interested in the location of these holes that are the countersunk holes that are on the plate. Now, because this part is so shiny, we will many times see this sort of reflective pattern when using our laser triangulation sensors off of holes like this. So this is a common phenomenon with very shiny parts. So, of course, we want to address that. We don't want that noise to cloud any sort of measurements that we're going to apply to these holes. So in this case, we apply the surface direction filter. And I will kind of skip ahead here to the results so we can see that the surface direction filter can very easily remove that noise and leave us with just this flat plane with the holes underneath. So let's just talk real quick about the settings that we've used to do that. So the minimum and maximum Z angle are essentially a clock or a sweep position. Do we want to focus on any particular direction on this scan? We don't. Since we're starting with a flat plate, we can just go for a full 0 to 360 degree sweep on this. Now, one thing I want to point out about the direction filter is think about it as excluding the things outside of the constraints that you put here. So what do I mean by that? I want to set these settings that I've got here to contain my flat metal plate. So don't think of it as excluding the noise in there, but rather we want to tell the filter which part of the data we want to keep. So that brings me to the polar angle. And the polar angle is essentially, in this case, an XZ angle. So this is what we might call the vertical angle from flat that we're dealing with within the scan data. So in this case, I set that polar angle from 0 to 20 degrees. And essentially what I'm doing there is I'm trying to tell the filter that I know I've got a flat plate in there that's basically parallel to the surface from which I started. I know that it'll fall within that 0 to 20 degree window, and I'd like to exclude everything else. And once I apply that, you can see that it's super simple. It's also removed some of the reflection that we saw on the outer edge because it too is vertical, and it just leaves us with that flat plane there. There is some embedded noise removal here too, and my colleague Mike Fisher is going to talk about some of the filters that are contained within other filters here, or other tools, if you will, shortly here. Okay, so that's the surface direction filter. And if we just do a quick review here of the ones we looked at, relative threshold. This is basically just isolating a particular area of the scan in a vertical stack, and we're doing that by a specific numerical or dimensional definition within that stack. So I'm saying I want to see an envelope between, in this case, 1 millimeter and 2.5 millimeters from whatever datum scheme I've created in my scan set. Percentile threshold, we're trying to accomplish the same thing, but we're just doing it in a slightly different way. So instead of defining a particular dimensional region, we're doing it by the percentage of data within that stack, if you will. Now, one thing I want to point out here is this is not doing anything laterally. This is just a percentage in Z, and that's why I keep referring to it as a column or a stack. This can be helpful if you've got, all kinds of different features in your scan set, and they could vary considerably both relative to each other and in the coordinate system. And finally, the direction filter, most often used for removal of noise that you might see in a pattern like we see in our example here, so that we can just isolate the surface, the flat surface that we started with here. Okay, with that, I'm going to turn it over to my colleague, Michael Fisher, and he's going to talk about some of the other filter capabilities we have.
All right, thanks, Chris. That was good stuff. So I'll start by highlighting that LMI is a 3D machine vision company. Every system that we sell measures height, but we do more than that. We can collect the 3D height map and point cloud data, but we can also collect 2D data. And the filters that we've been talking about so far can run on the 3D information as well as the 2D information. And there's some reasons why you might want to do that. And then I'll also point out here that we have filters for 1D or profile data. For more information on that, check out our first webinar. We went into those in quite a bit more detail. I'll just mention that we have 1D profile filters as well. All right, I'm going to stop the slide presentation and switch over to my emulator so I can show you an example of using surface filters for 3D data as well as the 2D intensity information. All right, so what we have here is a 3D scan of a portable music player. Really, it's the guts of the inside of a portable music player. You can see some really nice detail on all the components. I will point out that the color of each one of these data points corresponds to its height. In the upper right-hand section here, we show what the color indicates as far as a height value. So the purple and red features are high, the blue and green features are low. And I can spin this around and you can really get a feel for what the effect of that height difference is. So again, this is what we call the 3D height map, but I can also show some intensity information. This is the data that you would get if you had a traditional 2D area scan camera that sensed intensity. And I can actually turn off all my 3D information and just show my intensity data. When I zoom in here, you'll get an appreciation for the resolution that we're getting and what features you can see with the intensity information that you couldn't otherwise see with just the 3D height map data, specifically flat features like the text next to the resistors or the label with a barcode and some text on it. And as I mentioned before, we have surface filters that run on the 3D image as well as the 2D image. So let me add one of those right now for my tool configuration area. So these are all the different tools available with a Gocator. Today we're focused on filters, so I'll add a surface filter. And one that we haven't talked about yet is a negative filter, which is just going to invert the image. There's not a whole lot of practical uses for this. It's kind of a niche filter. In some cases you might want it, but it's a good one to illustrate using a filter on both the 3D height map as well as the 2D intensity data. So when we see the effect of this filter on our 3D image, you'll see the scan get inverted. Everything that's low becomes high and vice versa. Let's take a look at that. So you'll see what used to be low is now the high point on my part. That's what happens with your 3D data. And now if I check use intensity and switch over to my intensity information, you'll see that get inverted as well. So now my barcode, where before it was dark on a light background label, now it's light on a dark background. And since we mentioned it before, I'm going to show one of the profile filters as well. Let me go back to my 3D data and add a surface section tool. Right now, we just have a 3D surface, but if I add a section tool to slice my part, I'll generate a 1D profile. And I'll just slice it in an area where I've got some resistors. So we should see some nice profile data. Here's what that looks like. And this is the raw data from my surface section tool. I can now add a profile filter to manipulate that somehow. Let's say I want to average it out a little bit or a lot. I can change my averaging parameters and then look at that data, and where the profile started out really, really choppy, now it's been smoothed out with the averaging filter. All right, I'll switch back to my slides and move on. So Chris mentioned that we have some built-in filters with some of our tools. And this is because LMI has a wide range of inspection and measurement tools. And we find that for certain applications, when you're doing certain measurement or inspection tasks, you'll be using the same filters over and over. And so we figured, why not build those filters into the tools so you don't have to overcomplicate your program, set up a whole bunch of tools. You can accomplish your task with just a single inspection tool. And these are 3 examples of tools that use built-in filtering: Bounding Box Advanced, Blob, and Track. And here I have screenshots of the configuration parameters for each one of those tools, and you'll see optional surface filters built into those tools. And they're different for each one of these tools because the tools generally perform different tasks and require different types of filtering. So let's go through some examples. First example is what we call a Bounding Box Advanced tool. This is a tool typically used in the packaging or logistics industries to do part dimensioning. The tool measures a part's location, so XYZ location, its angle as well, and the length, width, height of the product. Generally, it's a box or some other type of rectangular product. And what we found when using this tool is it can be sensitive to noise. So it's often used in conjunction with certain kinds of filters, specifically percentile and open morphology filters. And so we built that into the tool so you don't have to, again, overcomplicate your program. Another tool that's really useful in the machine vision field is Surface Blob. Generally, we use this for inspection or counting. In this case, we're going to focus on the counting part. You might use the Blob tool to count bottles in a box or pills in a tray. Here we've got examples on the right side of counting bread product on a conveyor, or in the lower left, counting cells in an electric vehicle battery module. And with using the Surface Blob tool for part counting, it can be sensitive to parts that are touching. And so a good filter to use with this tool is an open or close filter to separate out those parts. And we've built that filter functionality into our Surface Blob tool. You don't have to use it, but it's available there within the tool without having to add a separate tool in your program. And the last example here is the Surface Track tool. This is a tool that we typically use in the consumer electronics industry, sometimes in automotive, to look at adhesive beads or a sealant. And with this tool, you're generally looking at a bead at a specific height. So the height filter works well. And then because the tool can measures really small areas, it can be sensitive to noise. So using a median filter to clean up that noise is good practice. And for the LMI Surface Track tool, we've built both of those filters into the tool so that it performs better. Every tool we've talked about so far is part of the general LMI machine vision toolset. When you download our emulator or use one of our Gocator laser line profilers, those tools are available in the toolset. But we have the ability to create custom tools, specifically custom filters for specific applications. We do this either through our GDK. This is a generally available Gocator developer kit. You can download it from our website. Plenty of customers take advantage of it to write their own custom filters for their applications, or you can have our engineers develop, based on an image set, develop a custom filter to remove noise or enhance specific features. And 2 examples of that here, something we, for a customer, called a spike noise removal filter, which removes interior noise that might occur due to reflection. You can see on the right, the lower right, the image looks a lot better if you're doing dimensioning. That's a much better image to work with than the image in the lower left, and that's made possible through using this spike noise removal filter. And another tool, we call this the Surface Histogram filter. It's kind of like a smart noise filter where it removes high and low noise without compromising the overall image integrity. So if you're doing high accuracy gauging, you're going to get the same measurement results of your part after that noise has been removed. It's not going to, you'll just remove noise without removing the important features on your part. All right, so we've spent the last 30 minutes or so talking about filters and how wonderful filters are and giving some examples of applications that really benefit from filters. But I'd be remiss if I didn't include some warnings about filters. We typically use filters as a last resort. There are some disadvantages to filters, and I want to point those out here. Number one, filters can be time consuming. Depending on how math intensive they are, depending on how large your data set, the filter can potentially hog a lot of processing time. And if you're working with a high-speed application looking at maybe 10 parts per second, that filter might not be able to run fast enough. So you want to be careful, especially using multiple filters or using a large kernel where every data point gets manipulated using a large neighborhood of points that can really eat into your cycle time. Also, filters alter your data. And many times that's a good thing because you're enhancing features or you're getting rid of noise. But that can also be a bad thing if you're looking for really small defects. Your filter might remove those. The image might look good to your eye, but you're removing things that are really important for your inspection task, or your measurements might not be as accurate if you're removing valid data. And in some cases, that data loss is irreversible. So after you filter your image, you can't get back to your original image and you've manipulated it too much. So just be careful when using filters there. At LMI, when we set up applications, we always focus on getting a good quality raw scan first and getting good raw data to begin with before resorting to image filters. There's a lot of ways with 3D systems that you can tune them to give you good scans, even of shiny, reflective, metallic material or translucent material or parts that might have multiple colors. There's a lot of things you can do with the exposure settings, potentially using multiple exposure times or your spot selection settings to get better data to start with. So, rather than, again, resorting to filters as, the first step, rather than going filter happy, work on getting better quality raw data. And with that, I think we can open it up for questions.
That's great, thank you. We do have one question, asking, where is the surface histogram tool located?
Yeah, so that was one of the custom tools that was developed for a customer. We have it available. I think it's in our beta tool set. This was developed for a specific application, so it hasn't been tested on all of our sensors on a wide range of images. That's typically how custom tools are released at LMI. So it's if there's a specific need for it, we can get that into customers' hands, and it will eventually make it into the general tool set. But it's a fairly new tool for us, and it was developed for a specific application. So it's not one of those tools that you can download as part of the general tool set.
That's a great question. Thank you for that. And Mike, thank you for that answer. And maybe just a follow-up question is, when you're talking about the dangers of over-filtering, maybe you could go expand a little bit more on what could potentially happen if you do. What are some of the things that happen if you're over-filtering?
Yeah, I think, and Chris can comment on this as well, but for me, I think in machine vision, there's often too much of a focus on getting pretty images, getting images that look good to our eyes, but that have important data removed from them. And so this is something we're very careful about, manipulating the raw data too much and losing a lot of valuable information. You pay good money for high resolution 3D systems. You don't want to just throw a lot of that data out or artificially manipulate it. So just because something looks good to your eyes after you've applied some image filters, it might not be the right image to detect the features that you're interested in.
Yeah, I think that's a good explanation. And, I always think of surface roughness types of analysis. If you apply filtering to a flat surface, for example, you can filter out all of that surface roughness that you're trying to detect. So, it can be dangerous. You want to make sure that you're maintaining that data accuracy that you're starting with. And this really comes back to what Mike said earlier, which is, you really want to focus on getting good raw data so that your results are accurate rather than just looking good.
That's great. Thank you. Yeah, and that's a very, very important thing, which is why I wanted to get a little more idea there. And we do have another question from David here. On the surface direction filter, did the region of interest include the surface itself, or was it placed just above the surface?
Yeah, it is. It includes the surface itself, and that's really important for the surface direction filter because, again, one thing I want to remind everyone about the surface direction filter is you're telling it what to keep, not what to get rid of, right? So it's important that your ROI contains the surface that you're trying to maintain. In this case, it was that flat base.
That's great. Thank you. And another great question. All right. So it looks like that's all the questions we have. Before we wrap up, Chris, Mike, is there anything you'd like to conclude with?
No, I'll just say thanks everyone for attending. Yeah.
Yeah, thank you. No, I think that does it.
Wonderful. Mike, Chris, thank you so much. And everyone attending, thank you so much. And again, keep an eye on your inbox for the video, the recording of this. It should show up in about an hour's time. Thank you very much again, and thanks for joining.
Thanks.